In part C, we're asked to find the first four non-zero terms and the general term for the Maclaurin series representing integral from 0 to x of f of t dt. And I put a copy of f of x on the workspace there. And so integral from 0 to x of f of t dt is just going to be a term-by-term integral of f of x. And so the integral of 1 is x minus x to the fourth power over 4, then plus x to the seventh power over 7 minus x to the 10th power over 10. And we were looking for the first four non-zero terms and then plus the general term. All we need to do for the general term of the integral is to take the integral of the general term of the original function. So we would have negative 1 to the n. That was a constant that stays as was. Then we're going to increase the exponent of x to 3n plus 1 and divide by the new exponent 3n plus 1. And so if we looked at our what we have here, and we put values for n above each term, 3 times 0 plus 1 is 1, so we would have x to the first power over 1. 3 times 1 is 3 plus 1 is 4, so we'll have x to the fourth power over 4, etc. And that seems to work fine. Now, in part D, we want to use the first three non-zero terms of the infinite series found in part C to approximate the integral from 0 to 1/2 of f of t dt. So, the integral from 0 to 1/2 of f of t dt really just means to put in x equals 1/2 into the integral that we found above. 1/2 over 1 minus 1/2 to the fourth over 4. And we want to use the first three non-zero terms plus 1/2 to the seventh over 7. And we're going to leave it at that. So actually the best way to do this is to say that the integral is roughly equal to, or approximately equal to, those three terms there. And so let's see what those three terms are going to be. We have 1/2, then that's minus 1/16 over 4, which is 1 over 64, and to the seventh power is going to be 128 times 7 plus 1 over, and by my calculation above there, 7 times 128 is 896. And alright, so use the first three terms of the infinite series found in part C to approximate the integral from 0 to 1/2 of f of t dt. And we did that. What are the properties of the series representing integral from 0 to 1/2 f of t dt that guarantee that this approximation is within 1 over 10,000 of the exact value of the integral? Now this is kind of wordy, but what are the properties of the series that guarantees this? One, it is strictly alternating. 2, terms decrease, and you can see 1/2 to 1/64 to 1 over 896 terms decrease in absolute value to 0. And that's good enough. That tells you that you can use the alternating series remainder theorem. And the alternating series remainder theorem tells you that the approximation, the error between the approximation and the actual, is less than the first excluded term, and the first excluded term would be the fourth term. Says the difference between actual and estimate is less than 1/2 is the value of x to the 10th power over 10, and 2 to the 10th power is 1024, times 10 would be 1 over 10,240, which is less than 1 over 10,000, and we're done. So because this is an alternating series, that's what they're trying to get at here. Because this is an alternating series, strictly alternating, terms decrease in 0 to absolute value. Terms decrease in absolute value to 0, so the alternating series remainder theorem kicks in, and it says that the difference has to be less than the first excluded term, which is x to the 10th over 10, evaluated at 1/2 is 1 over 10,240, which is less than the given 1 over 10,000. And that does it for this part and for this problem.